So before we start, I just wanted to introduce Mahmoud. Mahmoud is a TA for this course. He's my PhD student, one of the smartest students I had over the years. He's very knowledgeable in dynamics. He's very good with DYNA, so we will do the session with him. I also wanted to say that this program, DYNA 6, is actually developed here at Western, but it is licensed to companies all over the world. So this software is used globally for the design of machine foundations. We developed the software here, and we sell it to companies and universities across the globe. So we have clients in every country in the world. Whenever they need to do design of machine foundation, that is the software that most companies use. So the learning you are getting here is a very precious learning. If you get a job, not only in kind of any part of the world where you have to design machine foundations, very likely that you need to use the program DYNA 6. So hopefully you'll enjoy this session with a very knowledgeable instructor, and you are learning a very, very powerful tool for the design of machine foundations. Okay? It's intuitive, so I think it's very easy, but I don't want you to be overtaken by this. You have to pay attention, and you have to keep what we learned in class. Everything that we learned, we should consider here when we talk about the different models, the selection of the model, the assumptions we made to develop the models, and how they impact the results. So that is very important. The tool is easy, but we always say garbage in, garbage out. So if you don't pay attention to the information you feed into the program, the results you're getting are not really working. Okay? So all the best. You have more?
First of all, I just like you to follow my steps and also make notes, because it's very important to take notes for this software during our session. Okay? Firstly, let's go here to menu. So we'll ask you to enter the first title. Example, you can say something. And the case, for our case, we have need to study together two cases, shell foundation and deep foundation. We will start with the shell foundation, so I will consider this case as the shell foundation. Okay. When you open it, first thing is to edit the setting. You can use the imperial units or the SI units. Usually you use the SI units. And you have the frequency unit. You can choose between radian per second, hertz, or RPM. For our example here, I have the speed in RPM, so I'm going to use this in RPM. Okay, the frequency unit. If you want to use hertz or radian per second, that's okay. Okay. For the output flag, there is equal input, we need this. There is a dimensionless result. This will normalize the result and normalize the response. So please don't check this one. You don't need to check this one. Okay? We will have to get the response in meter or millimeter or something like that. So we don't need the dimensionless result. The stiffness and the damping matrices, you may check this, no problem. And output draft, this draft will give you a very bad presentation of the result, so just forget about it. I will let you know how to extract your response and your stiffness matrix and okay. So we don't check this one, we don't need it. Okay. Second is analysis constant. For this one, as Professor Sham told you in the lecture, for the half space, usually we use safety factor for the half space, which is 2, right? damper coefficient, we usually use 50% of the damper coefficient for the hospital pumps. So recommended to use 50%. So we use this factor as 2. Okay? So next step is to edit the foundation. There is a multiple choice of the foundation type. All what we expect you to use just 2 of them, the half space and the pile foundation. The half space we use this for the shallow foundation, and the pile of course for the foundation. Okay? For our case we are studying the shallow foundation, so we are going to use the half space one. Okay? After you use the half space one, you will find here some choice also. Firstly, the embedded. Do you want this foundation to be surface foundation or embedded foundation? If you choose the surface, it will be like that. If you choose the embedded, you will see here that increase the side layer of the soil. Okay? For our case, I will assume that our foundation will be embedded. Okay? Secondly, the footing shape. Is it rectangular or circular? For our case, for our example here, I will assume it will be rectangular. So usually it will be rectangular. And one of the assumptions of the half space theory is the footing will be rigid. This is of course, so I can't change this one. And just press OK. You press OK, it will give you this window. First one is the footing. This is the footing here. And you will get this one. Okay, so now you can use your input, you put a mass, X, length, all of the information, but this is very difficult to do manually. So usually we don't use this. What are we going to use? We're going to use the calculator. This calculator. Just press and calculate. And now we're going to feed the software with our geometry, the dimensions, and the software will automatically calculate all this information. The mass, Ix, Y, whatever you want. Okay? So let's start. I will assume that we have here a foundation. This foundation consists of mainly 3 parts. The main foundation here, which is 7 meters by 14 meters. So it's black here. So I will assume this is the X, Y, and this is the Y direction. Okay? X direction and Y direction. For the elevation, it's also the X direction, and the other one is the Z direction. Okay? This is the elevation. And I will have here 2 bed stands. Everyone is 5 meters, and the width is 1 meter. The elevation of the height is also 1 meter. Okay? This bed stand usually we put it above the foundation to help the equipment. Or we can use the equipment above the foundation. Okay? So we have here the foundation and 2 beds. Is that clear? Okay. Let's go to the DYNA and try to define this foundation. Okay. So when you are in DYNA, you will find that you need to define the corner X, corner Y, corner X, corner Y, and corner Z. It's very recommended that you choose the corner which is the in the left side, the lowest point. So it is this one. This point, it's highly recommended to use this point. Why I'm using this corner as the main point, as the 0, 0, 0, as the origin point, because after that I can define all the other points in all the other dimension in positive sides. Okay? If you choose, like for example, this point, all the other dimension for the 14 meter, you need to define these coordinates as negative 14 and negative 7 and negative 2 and so on. Okay? So to make it easy, we choose these points here, the lowest left point. Okay? So we're gonna start with this one.
Length 14. Width 7.
Okay, so here I define the foundation length is 14 meter, the width is 7 meter, and the height of the foundation is 2 meter. So I find it 2 meter. He asked you for the density. He asked you for the density. It's not the midway. So we're gonna use for concrete. It's around 200.
Okay.
2,400 kilogram per meter cube. Okay. So we're gonna use this value. 2,500. Don't forget that we are using the SI unit. So for the SI unit, the mass is in kilogram per meter. Density is kilogram per meter cube. Okay. So I choose this one as 2,500. Okay. If this is the only one, the only foundation you have, it is blade. That's it. You're gonna assume. Sorry. Again, let's play it.
Display.
Just press on display here. You can assume from here. Zoom from here. Sorry.
How it's gonna.
And for this is a plan. So we have here X, Y, and we can see the Z direction. If you want to see the Z direction, put here 90, and it will give you the X and Z. Okay? And you can also see it in 3D. You can see it in 3D. This is the first foundation, the middle foundation. Okay? You have any question?
No.
How did you get from that page before to this page? Like when you had the.
I just press on display. Yeah. Okay.
Where is it?
Okay. You guys have any question? Yeah. You actually didn't get to make him understand, just press on this here. Here. No, no. Now we can play. I feel like you're still giving it information.
Sorry.
Okay.
Son colora. Sorry.
Are you okay?
Sorry. Sorry.
Okay, so
Hello?
if this is your only
What's
foundation,
his name?
if this is your only foundation, you are good to go, and you can use this calculate here. It will give you the mass and y x x and y y all this information you need to know. Okay. From calculating.
Sorry, I have a question. One moment. Could you? Yeah.
Display? Nothing here?
Yeah, the numbers just add up. See the number again changed. Oh yeah.
Okay. That's it. Okay.
We did the same thing, it didn't happen.
I'm lucky.
Neither did I.
Okay, guys. For our example, this is not the end. We still have two bit styles we need to define them. So I will start with this one. The coordinate for this one, the x will be 1 meter plus 1 meter, and the y is also 1 meter. Okay. So for this one will be 1, and because of this bit style sitting above the foundation, so the corner z will be 2. The length of this bit style in x direction will be 1 meter, and for the width is 5 meter, and the height is 1 meter. Also, it's a concrete, so we're gonna use the rest of the same. For the other bit style,
Same density?
the corner will be 12, 1, and 2 again. The length will be again 1 and 5 and 1. Okay. Make sure after you define all the values here, you just press on any cell, another cell here. That's how the software will understand you are done your input. Okay. So after you do that, just display here, and you can find. And you can find your foundation here, and okay. Is that clear?
Yeah.
Do you have any question? Let's go back to the page.
چه سافتور سخت کاریه.
What? Okay. Next step, you will find here, this is the block where we define the rectangular shape for the foundation. And if you have a cylinder, you can define it from these cylinders. Okay? We don't have thin cylinders, we have all rectangles, so we just want this one. Next one will be the masses. The masses, if you have a mass you want to introduce, you can do that through this mass tab. I just press on the mass, and here you can tell your coordinates. So I will assume for this example here that the only mass will be the mass of the equipment, and this mass is sitting at a height of 3 meters above the foundation surface, and the mass will be 250,000. Okay? For this example. So will assume that this mass will be in the center of the foundation. The center of the foundation and sitting 3 meters above the foundation. 3 meters above the foundation. So the X for the center of our foundation here, for the center here, our X in X direction it will be 7. And for Y direction it will be 3.5. Okay? So we have here 7, for Y it's 3.5, and for Z it's 3 meters above the foundation. So we have the foundation 2 meters and 3 meters for above the foundation. So we have this mass will be above the foundation with 5 meters. Okay?
And the mass.
The mass again, we need to define the mass in kilogram. It gives you everything in kilogram. I just put it here. Okay. If he in your example or in your project or assignment, whatever, if he gives you the IX, IY for the equipment, that's okay. Just define it here. On our case, we don't have this information, so we just neglect it and just define the mass. Okay? Again, after you're done with this step, you can again display it. You will find here. You will find here. This point, this circle, this small circle in the center here. This is the mass we just defined. Okay? So if we put it like 90 here, in the elevation, you will find it 5 meters or 3 meters above the foundation. So 3 meters above the foundation. Okay? This is the mass we just defined. Is that clear? Okay. After you define the mass, I'm going to do the RBC. What is the RBC? What's the RBC here? What is the RBC here? Rectangular base center. This is the rectangular base center. What is the rectangular base center? This is the part of the foundation that is in contact with the soil. So for our foundation here, you all can know that the part will be in contact with the soil is the lower part here, right? I just want you to know the area that will be in contact with the soil. So it's 14 meters and 7 meters. Is that clear? Again. 14 and wide is 7. And I need to define the base center of this area. Okay? So I just need the point of the center of this area. So as you can see here, we have here 14 meters and 7 meters in the other direction. This is the dimension, and for the center of this foundation, you will find the center is 7 meters from here in X direction, 3.5 in Y direction, and for Z direction it is a 0 because it's the lower part of the foundation. Okay? So when here, base center will be 7, base center Y will be 0.5, and over base center Z it's 0. Okay? So this is the RBC, the rectangular base center, which is the part of the foundation in contact with the soil. Next step is to define the forces. Okay? Maybe this part is the most difficult part in the whole software actually. And I will tell you some rules about it right now, and I will tell you some about 15 minutes later. Okay? So just keep in mind, it's not the end. It's not the end of the problem. Okay? We're going to define the forces for this example here. It's telling you that the using machine is a rotating machine and this rotating machine, it produces a quadratic harmonic loop with maximum amplitude of 10 kilonewton. And this 10 kilonewton in both y and z direction. Actually, in this example, I tried to make it simple for you as possible. So I told you in y and z direction. Usually, as you know, there is no direction and no forces in the longitudinal direction of the rotating machine, right? So if it's rotating like that, there is no forces in the longitudinal direction, right? So there is no force in the x direction. We all know that. Usually, he told you that we have the forces in lateral direction and in vertical direction. When he told you this statement, you know by yourself that he means that lateral direction is the y direction, right?
Yeah.
Because due to the rotating, there will be a force in y direction. You get it?
Mhm.
Is that clear? Sure? Okay. So for example, I tried to make it simple and I told you directly that the forces will be in y direction and in z direction, and in both direction it will be 10 kilonewton. So I would assume that these forces will be in the center of the equipment exactly. So our x will be again 7 and 3.5, and the z will be 5. So it's the same point as the mass we defined. For the fx,
Zero.
I just told you that the fx will be 0, and for the fy it will be 10 kilonewton. But don't forget that we are using the SI unit. The SI unit is in Newton, so we need to define these forces as 10,000. And the same thing for Fz. Okay? For rotating machine, usually we don't have mx moment. We don't have moment at all. Mx or my. If you are defining the reciprocating machine, you may have mx, my, and mz. Actually, if he gives you this value, you can define it here. But usually for the rotating machine, we don't have any moment. Okay?
I've got an error on my statement. Same error.
Okay, sometimes it clash. I'm sorry about that. Just did you save? Okay, try to save it. Okay. So guys, whatever we define in this window here, we can save it separately. So just press save, and I can name it, for example, shallow foundation. And this shallow foundation will have extension of 3DF, which is 3-dimensional foundation. So I can save it for later. Okay. After we're done with all this, guys, I'm sorry. Okay. So we have here, after we define all our information here, just calculate. And when you are done, just close this window, and you will find the software automatically define all your information in the main window. Okay?
Where did you close?
Just close it to find all your information. So as I told you, you don't have to define all this manually. Just input the geometry of the foundation, and the software will do that for you. Okay.
Sorry.
Did you just close the page, like, press on X?
Yeah, did you save it?
No.
Okay, so, condition.
Close it?
Same values, right? Okay, so close this one. Okay, so, let's calculate.
No, I'm sorry. Sorry. I said it, didn't calculate. So you didn't know this.
So let's calculate. Okay, just close it and close the window here. That's all.
Okay.
It's asking if you want to save the file.
No, sorry.
I did this.
For the next step will be the side layer. As I told you, we assume that our foundation will be embedded in the soil, so we have to define here the side layers. Our foundation is 2 meters, so usually we can assume that the side layer thickness is 2 meters also, right? The side layer thickness. But usually Professor Sham preferred to assume it just 1.7, which is around 1 feet, 1 feet lower than the full length. Because he assumes that we can compact the soil in the upper part with to consider it in our analysis. Okay? So if your foundation is 2 meters thickness, you can use it up to 1.7 because we don't trust the compaction process in the upper part. Okay? I'm pretty sure he told you this information. Okay? For the side layer shear wave velocity, usually we choose the side layer because it's not the original soil. We're gonna use soil from our choice. So you may use the granular soil, you may use the structure fill or the CSLM. There is multiple choice, you can choose from them. For this example, I'm gonna assume that it will be granular soil. For the granular soil, usually the shear wave velocity ranges from 180 meter per second to 200 to 200. So I'm gonna assume it 100 meter per second. Okay. Next one is the side layer unit weight. We can assume that the unit weight is 20,000 here because it's in Newton per meter cube. Again, don't forget about the unit and don't mess with that. It will end up with very bad result. For the percent ratio, you can use this value 0.3, and for the damping, you can use this value 0.8.
4 point?
O two.
2%. 0.22.
Okay,
Okay.
السؤال اللي يشير بس صدق اشتغل.
We good here? Okay. Next step is the soil below. Soil below is the soil below the foundation, and as you know, this is the half space area. So if you have layered soil, you can calculate the best estimation or the average of this soil to get the shear wave velocity. You did this step in the assignment 1, right? When you have layered soil, you can calculate the average or the best estimation of this layered soil just with one number to present the whole soil, okay? The homogeneous shear wave velocity, okay? So for this example also, just wanted to make it easy, so we assume it's 350 meter per second. For the, okay, for the rate weight, we can assume it 21,000 meter cube, what's the ratio again, 0.35, and I will assume that the damping will be 0.03. Okay?
Option ratio
This is for the soil below.
0.35 and
Next step is the result. What is
damping
the
issue.
result?
I'm sorry, what was the damping? What was the damping number?
The damping?
Yeah.
0.03. 3%. Usually for the soil it's between 2% to up to 4%. You can assume between them. And in your project, Professor Sham will provide you this number exactly. So you don't worry about it. So I'll talk about the resultant here. What is this resultant? Usually the software will give you the response and the stiffness and all this stuff as the CG, as the center of the foundation. If you need to define more points, so if you need the response at the corners of the foundation, you can do that through this one, the result. Okay? So for example, if we need to get the response, the displacement, information in the corner of the foundation, I need to define this foundation, the coordinates of this point, the x and y and z. Okay? I will assume that we need all our response for the corner here, all the corner of the foundation, the upper corner.
14 or
14. 072.
14, 7, 22. So I'm gonna assume 2 points for the bed stand. 1, 5, 3, and so on. You can actually require the software to calculate the response up to 10 points here, up to 10 points. Okay? So I use just 5 or 6 points. That's okay, and I'll press okay and okay.
so we just see that
Do you have any question now?
Yeah, what was the 6 points
fifth and
coordination?
6th.
This is 113.
What is that?
What is the coordination of number 6? I just got the Y and the Z.
X was 1, I believe. Yeah.
113.
Let me check.
Thank you.
It's 1 right.
Thank you.
Okay. So the next step will be to edit the loop. We have here different type of loops. We have the hammer, transient, random, and harmonic. Usually you will use only the harmonic loop. This is what Professor Sham is looking for you. So just choose harmonic and press OK. Okay. You remember for the force we defined in the foundation, we defined the force is 10 kilonewton, which is 10,000 newton, right? You will find the same value, the software bring it to you here. Okay? The software bring it to you here. So we don't need to define the value of the force, but we need to define other stuff. For example, it will ask you about the frequency. What is the frequency of interest? For example, I will assume that the minimum frequency is 100 RPM and the maximum frequency 2000, maybe 1000, whatever. Okay? And the step frequency, I will ask him to do it every 50 frequency. So we will start from 100, 150, 200, 250, 300, and so on. Okay? The applied load in phase or out of phase, actually we have the load here is out of phase because we have one in Y direction and one in Z direction, and this is rotating machine. So when it's maximum in Y direction, it's zero in Z direction, right? When it's maximum in Z direction, it will be zero in Y direction. So it's out of phase. So I will choose this out of phase here, and we need to choose from here what is the phase shift. The phase shift, I will assume that it will be in Z direction, and I will get 90, so it's perpendicular on the other side. Okay? Just note this, so this is important. That's how you are telling the software that when the force is maximum in Y direction, it is zero in Z direction. Okay? So this is rotating the machine. It's going to give both maximum value in the both direction. The same value. Okay? Do you have any question? Okay. So the next one will be this here. Actually, he is asking you about your type of force. It will be quadratic or non-quadratic. Okay? So it depends on the type of load. If we have the load is reciprocation machine, this will be non-quadratic load. And it's not frequency dependent, it doesn't depend on the frequency. So what does that mean? If we have it in this machine, reciprocation machine, we're gonna choose non-quadratic, and we are good with this input. Okay? But actually, this is not our case. We have here the rotating machine. So we will change this later, but I just don't want you to be confused. So we will continue with this. But please note about that this is valid when you are talking about reciprocation machine. For the reciprocation machine, the load is considered constant and not dependent on the frequency. I will tell you more about this dependency on the frequency, but let me just skip this part. Okay? So I press OK, and now we are good. There is no other thing. Are we good now? So now, we're gonna run from here.
What happened?
Okay. So after we run here, we're gonna press on it, and he will give you this note telling you that the units you use, the damping safety factor, the foundation dimension, and what type of foundation you use, of space or pipe or something like that. As a total mass gives you all this information. You can find all this information. But actually, all these relative values not what you present visually. You need some visual curves and stuff. So we can get it from post processor. When you press on this post processor here, you can get the transition response at CG. As you can see here, it gives you the transition response. This is for Z direction and this is for Y direction. For X direction, we don't have any values for the load, so we don't have any response. And for Z direction, you can see from here.
Sorry, I'm getting an error.
Actually, the system doesn't respond.
Try calling again. It crashed sometime, I don't know what to do. You can't close it.
Oggi Hamisi istemiyor da bu şu ne oluyor? Bana hani yapmadı. Yani şu bu kutu şunu.
You must find something wrong. You check all this.
How much is this off?
How much? It's not much, bro.
It should be worth that
Response
So we have here, this is the
CNG.
transition and CG. As I told you, if you need the transition and at a certain point for the corner, for example, we define we defined here the transition at different points. So we find 6 points, the corners of the foundation, so we can choose which point we need.
Which point? Very Chirio.
Okay, so you can see from here, I'm showing you the vertical stiffness. The vertical stiffness, usually the vertical stiffness will reduce with increasing the frequency. So with the increase of the frequency, you will find this vertical stiffness decrease. Okay,
Normal traffic.
but this will not be the case for the horizontal. The horizontal will be usually constant. Okay, so you remember when Professor Sham told you in the picture that if we have the Mohsen solution for the soil, almost 2.5, the vertical stiffness may be, in this case, negative. You remember this information? Okay. Actually, I have two information I need to show you. Okay, so firstly, when we have here the transition from this curve, you might think that now you know. Now you can tell me what is the natural frequency, right? right?
Someone should have mentioned.
Can anyone tell me what is the natural frequency? Do you know what is that? Okay. The natural frequency of the foundation is the frequency. If you hit with your operating frequency, you will end up with resonance. Did you hear about the resonance? Okay. The resonance is the foundation will go crazy and perform multiplied, will have huge amplitude in all directions. Okay, so for this example, you can see the natural frequency from the curve, the pattern here. The natural frequency is the frequency where the foundation will show the maximum deformation. Okay? So we can predict it around 750, right? We can predict it around 750. If you want the exact natural frequency, I will show you how. Okay? So just let me show you how. Okay. So here in edit setting, for the damping safety factor, we assume that it's 2 because this is the right thing, and this is the actual response. But if you want to just get the natural frequency of the foundation, exactly the natural frequency, you can assume this damping safety factor any higher value. For example, 10 or 12, something like that. What you are doing here is you are killing the damping. You are killing the damping. No damping at all. So the foundation will check like crazy, and it will give you exactly the frequency that hits the resonance. Okay? So for this example, I just put it 10 here. Please just take notes on that. And press OK. And run the project again. Override OK, yes. Okay. And if I check again the concern response here, you will see it. You will see it. As you can see, now we can see exactly where the resonance happened. It's actually 750. Okay? So what is the importance of knowing where is the natural frequency of the foundation? What is the importance of that? If you remember our machine working in operating speed 900 RPM. 900 RPM. If we have this type of information at 775, imagine if this curve was at 900. What does that mean? That means that the operating frequency of the machine will be the same as the natural frequency of the foundation, and you will be end up with your foundation shaking like crazy. Okay? This is the importance of knowing where is the natural frequency. We need to keep our operating frequency away from the natural frequency of the foundation. Is that clear? Okay? So usually we can't change the operating frequency for the machine, but what we can do is to change the foundation. It changes the side layer. For example, we use granular soil. We can use another type of soil, CLSM, or structural fill, or something else. Okay? If the foundation is 2 meters, you can try to make it 2.5 to change the stiffness, and that will change the natural frequency of the foundation. You get the idea? Okay? So that we keep our operating frequency away from the natural frequency of our foundation. Is that clear? I hope it will be clear. I don't know.
Is there two natural frequencies here, or would you go with the Y?
Okay, actually we need to stay away from the Y and the Z. But for this case, the Z is more deep. This is the problem actually. So if you hit the Y, you will end up with this value of this one. If you hit the Z, you will end up with second time. Okay? And don't forget, this is just example, and I'll define a very little forces, 10 kilonewton, maybe 200 kilonewton, something like that, end up with a very high values. Okay, guys. So, in your assignment, in your project, you may need to do this step to show the professor or show whatever what is exactly the natural frequency of this foundation. You may need to do this step, but this is not the actual response. This is not the actual response. What is the actual response? As I told you, we should go here and edit the setting and put the damping safety factor as 2. This is the actual one. Run the project again and okay. You will end up with this response, so that if he asks you about the response, the real response of the foundation as a seizure or something like that, this is the curve you should provide in your report. Okay? Okay. So let's go back to the stiffness. As I told you, for the vertical stiffness, it reduces with the increasing of the frequency. If you want to see this vertical frequency become negative, we can do that from here. When I edit foundation, okay. Okay. What it changed when we changed the Poisson's ratio from 0.35 to, for example, 0.5? What do you expect to be changed? What is this 0.5 value? Okay, so this 0.5 value is actually represents the behavior of the water, the incompressible material. So when you push the soil in the vertical direction, it will behave the same in the horizontal direction. Behave the same strain in the horizontal direction. You can't compress the soil. This is theoretical value, so you don't expect to get this pattern in the real life, but just let me show you how can that affect the vertical surface. If I press OK here, OK, and run project again. Okay. So as you can see here, with increasing the Poisson's ratio up to 0.5, that will end up with will be negative in the high frequency. And I'm pretty sure also Professor Sham told you about this behavior and this phenomena.
بازی داره میکنه برای خودش رو ساخته یعنی ماهی چه میفهم چی گفته
Okay, so now
الكلام ده نجيب شوش خدش مصر
Okay, similar. If I wrote something here, you will see it?
Yeah.
You see this part here? Okay. So, okay, so for the rotating machine, actually, the governing equation of the rotating machine, Professor Ram told you this information in the first lecture notes. So for the rotating machine, the governing equation is F equal ME omega squared. What is the M? M is the mass of the rotating part, okay? Of the rotating part. What is the E? E is the eccentricity. So if the rotating part has an eccentricity of 1 centimeter, of 2 centimeter, this is the eccentricity that will produce the force. If there is no eccentricity at all, that means that we don't have any dynamic force. So we need the rotating part to be eccentricity, to have eccentricity like very small, 0.1, 0.2, something like that. Okay, so this is the eccentricity. And what is the omega? This is the operating frequency. This is the operating frequency. And actually, the rotating machine is behaving, the type of fluid is quadratic, harmonic fluid. So if you are dealing with rotating machine, you need to define the root as quadratic harmonic fluid. Quadratic harmonic fluid. So what does that mean, quadratic harmonic fluid? Quadratic harmonic fluid means that it's frequency dependent. It's a frequency dependent. So if the frequency change, the forces will change because it calculates the force based on the frequency square. Okay. So how can we get this? How can we use this information in the DYNA software and for our example? For our example here, we are using the rotating machine. So the way we define the force is not right. So we need to define it correctly. Let me show you how to define it. Okay, you remember this step when we define the load? When we define the load here, we defined all the 10 kilonewton, which is 10,000 newton. We defined all the load in this one, right? Actually, this is not right in case we are talking about the rotating machine. How can we find the right number here? The right number here, as I told you, for the quadratic harmonic load, the software will multiply whatever the force you give it with omega squared. So we need to just remove the omega squared. We need to remove the omega squared. Okay. So if we have 10 kilonewton, this is 10,000 newton. Okay. Divide this value by omega squared. For our example here, it's 900 RPM. 900 RPM multiplied by 2 pi and divided by 60, that will end up with around 180 radian per second. I'm sorry, just to check the number. No, it's not right. I'm sorry. This is 94.25. Okay. So 94.25. This is the omega squared. I will put this number here. 94.25 squared. Okay. So I will divide 10,000 Newton over 94.25 squared. I will end up with 1.13 Newton. 1.13 Newton. Some of you may don't understand what I'm doing here, but continue with me, you will understand everything, okay? Don't worry about that. Okay, so this value here, which I calculated right now, it presents the M multiplied by E, ME. This is the force. I will use this one here. I put it 1.13 and here 1.13. Okay? I will save and calculate and then close this one. Everything okay. Go to the load, harmonic load, and now you will find that the forces you input in the force before 1.13. You get the same forces here, 1.13, right? But this is something you need to change. Do you know what is it?
Quadratic.
What do we need to change?
From
Huh?
non-quadratic to quadratic.
The quadratic, right?
Yeah.
The quadratic. So we have here, we was introduce this as non-quadratic. Now we can use the quadratic frequency. What we are doing here, right now, the software will automatically calculate the force based on this information. You define the forces, which is solid, but it will multiply it by omega squared. You got it? You will multiply it by omega squared again, and you will calculate the total force. Some of you might think, what is the importance of that? You will end up with the 10 kilonewton again. No, this is not the case. Actually, we are studying the frequency starting from 100 RPM up to 2000 RPM. So the frequency change and also the force change with time. Okay? You got the idea? When can I use this method? When I must use this method if you are dealing with rotating a machine. As in our example. If you are using, dealing with reciprocation machine, you don't have to do all this stuff. Just to define the maximum force, and it will be non-quadratic frequency. Is that clear? Let me show you again. Here. Okay. From project, yes. You remember the previous pattern? Remember? The pretty changed now, right? But this is the right one. This is the right one. We defined it correctly this time. Okay? Is that clear? Do you have any question? If you are interested in the response, also you can get the response table from this here. Just press response, and you will find the response at the CG. It gives you the transition X, Y, and Z, and rotation also. Here the cut point that we defined already. If you want anything from it, and also the stiffness table, you can find the stiffness table here. Non relatively frequency.
아직은 괜찮은 신참사는 거.
Okay. So if we have here this foundation, and you are requested to study the shallow foundation and the deep foundation option to decide which one is better for you. So we are done here with the shallow foundation. I will do the next case. So we can go here from title, change the shallow foundation to, sorry, let me firstly save as, and it changes deep foundation, save, and then change the title from here, shallow to deep foundation, okay. Now we are ready. For the setting, it is the same, nothing will change here. Edit the foundation. What is the main difference in this one? We choose by, right? We'll choose by. Okay, because it's deep foundation, we choose by. He asked you about the embedment, if it's surface or embedded. I choose it's embedded again. In this case, it's not a shallow foundation, it's a pile cap, so the pile cap will be embedded in the soil. Again, the foot shape is rectangular, and it's rigid, everything is okay. Okay. The pile cap, we have the same information as the shallow foundation. If you are studying the same foundation, but either it will be shallow or deep foundation, you don't have to change anything with that. Okay, this is the same shallow foundation dimension. Okay, but this time we will define it as the pile cap. If you need to change something, it's okay. Press calculate and open again. And choose this shallow foundation option and change whatever you want. The masses, RBC, forces, anything you wanted to choose, and then close. Okay, everything is good. The side layer, again we have one side layer. I defined it as I defined it as granular fill in the shallow foundation. Let me this time define it as structural fill. The structural fill, as I told you, is a shear wave velocity for it ranged from 350 to up to 400. So we can change this T to 350. If you want to keep it as 180, that's okay. It's fully okay. It's granular fill. If you want to change it, it's up to you. You can actually study different cases to decide which one is the best for your foundation and for your operating speed. Again, I'm not gonna change the the side layer, percentage ratio, the damping ratio, all of them is okay. And let's go with the pipe. Okay. This is mainly the difference between the deep foundation and the shallow foundation, that you have to define the pipes. Okay? So, firstly, he asking me about the pile head condition. I will assume that it's fixed, so it's fully connected with the pile cap. The pile cap, I will assume it's floating, no end bearing. And for pile properties, I will define the pile length as 10 meter, whatever. The pile unit weight, I will assume it's from concrete, so the unit weight is 25,000. And for the static load, actually you can calculate the static load from the mass of the foundation and the mass from the base stat, equipment, all this stuff, and then divided by the number of the piles, but we don't have to do that right now. This is just for example. So I will put this 100,000 Newton. The Young modulus for the concrete, the elastic modulus is around 30 gigapascal, so I will define it 30 and percentage ratio is 0.25. The damping 0.01 is for the concrete, and for the rigidity coefficient dimension is the pile shape, and for the circular pile, this value you can use it 1.12. For the square, it will be around 1.2, and for the rectangular pile, it will be 1.25. Usually we don't have square or rectangular pile, so 1.12 is okay. Okay? So now you can define the pile coordinate, the x and the y by yourself, manually. But this is not the case you will do. This is very difficult actually. So we're gonna use this here. The mesh one. Mesh cap. You see it? Mesh cap. Press the mesh. He will ask you what do you want to find the title here. I will say it's deep foundation.
Mesh type,
Okay. I will choose rectangular mesh. Rectangular mesh. He will ask you about the starting pile, the pile coordinates, the starting pile, the first pile. Okay, I will define it as 0.8 and 0.8 also in y direction. The ending one is 13.2, 14 minus 0.8, so it's 15.8, and it's the same here. It's 6.2. And it's equal spacing. The number of piles, I will assume that the number in x direction will be 6, and the number in y direction will be 3. Okay? And it's equal spacing. It's equal spacing. In y direction also equal spacing. Everything now is okay. Okay. Now, after we just press close, you will see the coordinates of your pile. Okay, so if you press trigger here, if you press figure, you can see actually your piles here. We have 3 in y direction and 6 in x direction, so it's 18. And every one of them, if you get close to it, you will find the coordinates for this. Sorry.
in your end pile blackboard?
Sorry?
The 6.2.
Yeah, he changed it a little bit because of the
Esto está en su picture.
Okay. So next step here will be the pipe soil. The pipe soil here. If your pile has different cross section, you can use this one to define the pile and define the different cross section all over the length. For our case, the pile has only one cross section, so this is not what is the rest. But actually, we're gonna use this window to define if we have a layered soil. So we're gonna assume that we assume that the pile is 10 meter, and I'm gonna assume that every 2.5 meter there is a different type of soil. So, for example, I will assume 4 layers here: 2.5, 2.5, 2.5, 2.5. Don't forget to choose a circular solid here because it's a concrete pipe, so it's circular solid. And the pile radius, I will assume that this pile radius will be 0.4. So the diameter is 0.8, 0.4, 0.4. And then I will press calculate. It will calculate the area, the x inertia, y, and the inertia. Okay? After we define these layers, we can use this layer in the soil element here. So that if you have different soil layer here, you can define it from this layer. Okay? So I will assume that the first layer will have shear velocity of 200 meters per second, and joining it will be 8,000, Poisson's ratio 0.3, and the damping 0.23. Again, dumping 0.22 for all these soil layers. And Poisson's ratio 0.35, 0.25 for example. Unit weight will be after we define the applied soil, we can find now the soil below. This is the soil below the pile depth. Below the pile depth. So let's assume it good soil. Just shear velocity around 400. The soil liquid is okay. 21,000, 2.3. Okay. And the dumping ratio, we'll assume it 2.2. Okay. Okay, so for the output here, you can get again the resultant. If you need the response at different location, you can choose these locations from the resultant here, and all the other option we are not interested in. There is placement, actual load in the pile. All this information we don't need anything of it, so just neglect it. Okay? And press OK. The load, we're not gonna change the load. We have the same load and everything is okay. And we can now run the project. Again, here is the response transition for the pile foundation. And now you can compare this result with the shallow foundation. Actually, I believe that in your project and in your assignment 4, Professor Hisham will ask you to do this exactly, to do the shallow foundation, compare the shallow foundation, and to compare with the deep foundation, and comment on which one is better, so you can choose the response, the T-scale response, and show which one is response is better for our case. And you can also try, as I told you, with the side layer. This side layer will be granular fill or CLSM or something else, whatever. You can study all these cases. That's all. If you have any question, if anything unclear, want me to repeat something again, I'll be happy to do that. And
Thank you.
I'm done.
Thank you.